All right, let's get started. So, good morning, everybody. Thanks so much for being here. I am super excited about today's session. All right, I want to ask you all a quick question. We're just going to do a quick poll in the chat. When you think about hydrogen aviation, what is the biggest barrier? It's multiple choice: technology, infrastructure, or policy. I will put your choices. What is the biggest barrier to hydrogen aviation? Just put your answer in the chat. What is the biggest barrier to hydrogen aviation? Lots of infrastructures, a technology, money, maybe. See, I think that would come down to policy. I would agree money as well. There's no right or wrong answer, but yes, if you didn't hear the question, go ahead and put what's the biggest barrier: technology, infrastructure, or policy. Stick your answer in the chat. And you can do that at any time. I just heard a weird noise. Make sure that everybody's muted, please. And so the reason I asked that is because over the past, gosh, over 3 years now, I can't believe High Sky is that old. We've often said infrastructure, policy, and technology as well. Thinking about like storage and things like that. But the more we kind of got our hands dirty and got into the nitty gritty, we realized that there was a really big gap in policy, not necessarily for anything bad or nefarious, but just simply because most of us are aerospace engineers and we're very focused on the technology. I just saw that. Scion, I see that you joined. I'm going to make you a co-host so that you can let people in so I don't leave them in the waiting room. Okay, hopefully you heard me, Sam. I just made you a co-host so you can let people in if you hear that doorbell sound. Doorbell sound. So anyway, we just, a lot of us like to focus on technology and infrastructure, but I started noticing that a lot of the people that were working on the technology were having some frustrations with getting funding, whether that's private capital or public capital, and just kind of a lot of barriers to entry. And so I interviewed David Smith recently, the CEO of Robinson Helicopter, who, as many of you know, is working on hydrogen powered helicopters with United Therapeutics subsidiary Unither Bioelectronics. And I just want to play you what he said.
I've seen this more and more. I mean, Robinson's history, I've never had lobbyists ever in our company's history until this last year. And we felt like it was necessary for some of the work we're doing on the defense side of the business, and that's most unmanned and manned aircraft. So we did that, and it's been very successful. A necessary part of our democracy. If you want focus in the legislative process, you actually have to put professionals at it and spend time doing it. I think that's an appropriate way to do it, and say that High Sky and all of our members can go and say, let's go ask for government appropriations that prioritize this amongst all the other priorities, at least a little bit. So there is money that can flow in this direction. And I argue, I tell people why I like this. One of the things is that it goes right alongside investments for AI and data centers that we know is going to be a big part of our future. Let's team up to say, let's make affordable or more sustainable power production locally. And then as part of that, let's explore hydrogen production locally and infrastructure spend on that. And then that opens up all the doors for hydrogen as a regular general aviation fuel. I've seen this more.
Okay. So yeah, I really took that to heart when he said that. And those were some of the, the barriers that we were finding. And so I want to ask you one more question. If High Sky, because a lot of you didn't, I don't think any of you answered policy on the last question, but I'm starting to believe that policy, it kind of starts there. So if High Sky organized a hydrogen aviation advocacy day fly-in Congress, like David just described, where we would go in, all of us together, and advocate for appropriations in the space, would you want to be part of it? Yes or no? Drop it in the chat. We got one yes. I want to see. We have one no, one yes. Gabriel, I'd love to hear why you said no, but we can save that for later. Maybe I'll have a one-on-one. But yeah, if you're interested in joining us to advocate for hydrogen aviation, and advocating for appropriations in this space, do you want to be part of that? It's not a trick question. Would you want to be part of that? Yes or no? Drop it in the chat. Or you can put a 1 for a yes. And some of y'all may have moved off to multitasking, but it would depend. Okay, good answer. That's a very good answer. Yeah, you can put your own answer if you have your own, but would you want to be part of it? And I should maybe say depends. Okay. Let's say, well, let me just move on to why I asked you that. So if you said yes, then you absolutely need to be part of our policy cohort, which is we're doing exactly that. And it's a combination of, and hopefully I answer some of what it depends on, but it's a combination of like policy 101 lectures where we kind of understand like what policy is, the difference between advocacy and lobbying, what we can do. Then we talk about the state of hydrogen aviation appropriations right now. And then we actually follow up with a capstone project where we actually are having an advocacy day. So we're going to learn how to do it, and then we're actually going to do it. It's 100% virtual. So if those were some of the things, yes, I know, Ken, you are in Canada. We actually have a couple of people not in the US participating because they're wanting to learn more for about the US policy. But anyway, that said, so we've launched this cohort and we meet on Tuesdays, and tomorrow we're hosting the lecture Understanding Policy Gaps in Hydrogen Aviation and what to do about them. And that lecture is what you saw right here. And it will feature Dr. Ashira Butler Green, Dr. Philip Ansel, and Elias Waddington. And they are some of the brightest minds in this space. So you won't want to miss that tomorrow. That'll be a 2-hour lecture, and I highly encourage you to attend that. And let me give you the registration for that. Don't worry, I'm almost done with my spiel, but you can register for free to that. And what they'll be presenting is they just wrote a white paper. They just published a white paper, the three of them, titled Evaluating Readiness for Hydrogen in the United States Aviation Industry from a Policy Lens. And so they're going to go over their findings from that paper. I cannot wait. And I guess I could give you a link to that paper if you're curious to check that out as well. I think you have to pay like $40 for it or something, but there's the link to that paper. Okay. So now let's get into today's session. Well, okay, wait, before I do, does anybody have any announcements or anything that they would like to share about upcoming events? Ken, I know you did some exciting things around hydrogen lately. I know you haven't like officially written it up, but would you like to come on and share what you experienced in Canada?
Okay, so I just attended the Aero Montreal International Aerospace Innovation Forum that occurred last week in Montreal on Monday and Tuesday, attended by over 1,000 people. It's the
Wow.
largest aviation conference in Canada because 40% of the Canadian aerospace industry is located in Quebec, where you have major OEMs like Bombardier, AE, Pratt and Whitney. Airbus has a production line for the A220 and a whole cluster of other companies. There are a number of things going on in advanced air mobility in Canada and centered in Quebec. There's a new cluster combining 3 airports in the Montreal area: Mirabel, Trudeau Airport, and St. Hubert Airport, now named Montreal Metropolitan Airport, where they're part of an aerospace innovation zone. And at Mirabel, a number of companies are locating research facilities. They plan to have an RPAS or a drone test area, etc. In addition, Canada is pushing to increase its defense spending beyond 2% and up to 5%. So there's now a new defense industrial strategy. The combination of an earlier strategy on sustainable aviation by 2050 and the defense industrial strategy has spawned a number of initiatives that include hydrogen aviation. One is H2 Can Fly, which was initiated by the National Research Council and now has been spun off from the National Research Council. And that's to create a national ecosystem for hydrogen aviation. And one of the plans is actually to have a full-scale aircraft demonstration aircraft using a BAE 146 4-engine airliner. That's a longer-term thing. A second initiative is there's an organization called Strix, which administers the Sustainable Aviation Fund, And then their latest
Strix? Spell that.
STRIX. It's apparently an owl.
Okay, I haven't heard of them before.
They were known sort of as Instead, which
Mm.
was the Sustainable Aviation Fund, but they're receiving an additional mandate for defense R&D initiatives, so they decided to pick a higher level name because eventually they'll have two pillars, one dealing with sustainable aviation innovation and another one dealing with defense innovation. So Strix administers a fund, and the grants are allocated to an industry partner with an SME, and partner with an academic institution. They announced the fourth round of funding last Monday, and for example, Pratt& Whitney has received support for hydrogen aviation. I'm not sure if it's hydrogen combustion or hydrogen fuel cells, and some of the earlier funding rounds have also included hydrogen. There's also National Research Council of Canada just received a funding increase of $800 million Canadian, which is probably a lot. Well, it's a lot less than US dollars. That includes a number of initiatives. They're buying a global business aircraft as their modern test bed. They're going to be setting up a drone innovation hub. One of our VFS board members, Derek, has stepped down from the board of VFS simply because of workload for that new initiative. And so it's getting confusing because there's multiple alphabet organizations embracing sustainable aviation, advanced air mobility, and hydrogen is a component of a number of them. And it all seems to be happening at once, but actually the seeds have been planted over many years.
Yeah. Well, cool. Thanks so much for sharing. For those of you that aren't familiar with Ken Swartz, he's an esteemed High Sky board member as well. After I literally twisted his arm and told him he needed to support hydrogen aviation.
And I have to actually give one more plug.
Yeah.
I'm also the co-producer of the 20th Annual Electric Aircraft Symposium, which is being held at the University of Wisconsin Oshkosh on the 18th and 19th of July, which is the weekend before EAA AirVenture, which is held at Oshkosh Airport, and last year attracted over 700,000 people and 10,000 aircraft. Earlier today, we issued the press release for EAS 2016, and we were pleased to announce that Aero Friedrichshafen, which is the big European general aviation trade show, which begins this week, has joined us as a corporate sponsor and partner.
Exciting.
So they are cross promoting EAS, and we're promoting their event. And at Aero this week, there is a large sustainable aviation presence through 9 exhibit halls, and hydrogen aviation is featured very prominently at Aero. So that's a boost, and we have some hydrogen aviation people speaking at EAS in July. For anyone who's interested, finding accommodation in Oshkosh is a real challenge. Easier on the weekend before AirVenture, but if you're looking for accommodation, you might have to look up for a second location if you plan to stay on for AirVenture, because with 700,000 people coming into a town of 55,000, you have to look at commuting or alternatively camping.
Yes. Thank you so much for sharing that. And you made me remember also this month, I don't know if I have a date on here, but to our Ohio folks and people in that region, High Sky partnered with eVTOL Insights for their North American Conference and Awards, and we are so happy to announce that there will be a hydrogen aviation session featuring Chris McWhinney from Millennium Rain Energy, Vadim Lovich from NASA, and Jared Semick. I think Jared and Vadim are both and Jared's from Ethereum, Eternium. I'm going to get it, Jared, one of these days. They're both with, they are both on this call is what I was going to say. So let me just stick a link in the chat for that one. And then also, Ken, you probably already sent me that press release. Feel free to post that on our website, and I can also share it as well. Okay, so now to our speaker. Okay, so yes, I am so excited for Dr. Ahmadreza Rahbari, who is the Director of R&D at XinTC, operating at the intersection of hydrogen systems, techno-economic analysis, and business development. With nearly a decade of experience in applied energy technologies, he specializes in translating complex hydrogen systems into clear, decision ready insights for projects and stakeholders. Without further ado, please welcome Dr. Rahbari to the virtual stage. And Dr. Rahbari, the stage is all yours.
Thank you very much for the introduction, and I'm happy to be here. And thank you for the invitation. Greetings to everyone from the United States and from all over the world. So, for today, I'm going to give an introduction to our company, also our product, and I will link that to how scalable hydrogen production we see that as a company, how our solution is. So, for that, I will share my presentation with you, and I will take it from. Is my screen visible?
Yeah, you just need to go. There you go. Perfect.
Yes. So our company is Exintek. We are a Dutch original equipment manufacturer of modular alkaline electrolyzers. We are in Europe. It's located in the map. We're a tiny country, but Netherlands is a very highly innovative country. Following up on that, Exintek has developed a disruptive technology for alkaline, modular, scalable alkaline process. So we have 3 locations in the Netherlands. Our scientific center from which I am joining the talk is in Delft. You may have heard of the university in Delft, TU Delft. So we are very close there. I've also done my PhD there. So there are some good connections with the knowledge institutes with us. We have a hydrogen hub where our hydrogen system is currently operating, is in the middle of the Netherlands, is outside of Barneveld, and our head office is closer to the German border. So the Netherlands is small. Going from one side to the other may take about 2-3 hours. So it's not that far away compared to locations in the US. So looking at the market, before jumping into the electrolysis, I want to put a little bit of perspective how Exintek sees the market. Basically, we arbitrarily divide market into 3 segments. So we look at residential market and the large industry. For large industry, you can think of steam methane reforming market, high volumes of hydrogen or natural gas needed. You're talking about constant loads for producing really at gigawatt scale. Residential market we see as individual households, maybe 150 kilowatts, 200 kilowatts maximum. And whatever is kind of in between is for us the middle market. So these are medium to small industries, are still depending on energy sources from different kinds, either electricity or natural gas. It can be also ammonia. And these are the industries that need to become green with time. So it can be from policy side, also in Europe or at the European Union level, there are policies to move towards a green industry. But it can also be the incentive of the company or of the business itself. And what happens is these industries are not necessarily centralized, or these companies. So you want to develop systems that can serve these industries in a decentralized way, relying on sustainable energy sources such as solar energy or wind energy. As you may know, in many locations, you may have grid capacity limitations. So basically producing that amount of hydrogen, you may not have the available grid structure to do that. So if you can think of a system that can be flexible enough to work with flexible power, and you can scale it because it's standardized, so it's modular, you can easily scale it, and you have a low maintenance system. You can set up decentralized locations and you can produce hydrogen, and you can also consume it at the location. And of course, you can also transport hydrogen. So that brings me to the next slide. So of course, by hydrogen, we don't mean everything is about hydrogen use or hydrogen production within the renewable energy landscapes. This representation kind of estimates or makes an estimation of which industries are really hard to abate, or some of them cannot work without molecular hydrogen, fertilizer, hydrogenation, hydrocracking, desulfurization. There are no real alternatives for them. And there are some industries that are between jet aviation fuel, shipping, that they have a good chance that hydrogen becomes more at scale in these industries as well. So these are in transition. And there are some industries or some applications that either better off with full electrification, or it is still non-competitive for hydrogen technologies to take over fully. So for us, for Exintek, we generate hydrogen from our systems for any application, for any location in the world. So I will do a more deep dive into that. For us, the application doesn't matter because we have certain modular components for our system that we can adjust the quality of hydrogen and the pressure of hydrogen to that specific application. And that's the useful thing about having a modular system. So I'm assuming the audience are familiar with electrolysis, but very at high level. So basically generating hydrogen with water electrolysis requires metallic electrodes and applying electricity as you see in this schematic. So by applying that, especially I'm talking about alkaline technology. So there are other technologies such as PEM and an ion exchange membrane. I will touch on that briefly, but keeping alkaline as a basis, we have a reduction of water on one side, and then there are ions and charge forming, and these charges are swimming to the other side, to the other electrode, and at the other electrode, oxygen molecule is formed. So kind of the performance of the system really relies also how this cell is made. If these electrodes are really far away, these ions have to swim really far distances. That means electrical resistance, and that kind of affects your performance, the performance of the electrolyzer of the system. So there are lots of design considerations. There's also conductivity of water. Do you don't use pure water, of course, for alkali. So there is you use a solution of potassium hydroxide typically to help reduce the conductivity of the system, and what kind of distance you have. These are all kinds of design questions and design considerations that we have as a company or other electrolyzer manufacturers as well. They need to think about this together with the application to come up with a system that works well. So we are heavily focusing on wind and solar integration for alkaline. And that's the disruptive part of our technology, because you may know classical alkaline from the market is mostly designed for constant loads, doesn't really like on and off cycles, large stacks. We have this specific technology. We have a different variation of alkaline that allows us to go with profile of wind and solar energy. So that means like we have to consider performance, choice of materials for us is very important. It has to be a durable and sustainable system. So we have made fundamental design choices for that. And I will be going into these fundamental design choices as we move forward. So basically our mission is we want to generate hydrogen at the lowest possible cost price. This is for us key. Interacting with the market, there are different perceptions, maybe from a more conventional point of view. There are discussions about capex and opex, which are of course relevant, or there are purely discussions about efficiency of the electrolyzer. At the end, what we see for bankability and having the projects become a realization, you need to look at the cost price of hydrogen, how much per kilogram of hydrogen you can generate this in dollars or euros. So dollars per kilogram of hydrogen or euros per kilogram of hydrogen is the decisive factor for the financing, because you can map your financials, the money streams, the costs, revenues. And for Exintek, the goal is not to make the most advanced or the highest efficiency system. It's entangled with a lot of design choices to keep certain critical materials from our system because of scarcity or because of geopolitical limitations or value chain limitations. Keeping everything in balance, we want to come up with a system that generates hydrogen at the lowest possible cost. That also means not necessarily for our system, how we connect to the renewables matters. So the less, let's say, intermediates you have between your energy source and the electrolyzer, the fewer losses you have. Example is having electronics between your solar field and your electrolyzer for decentralized solutions. We have eliminated that. So we can have a direct route from a DC source like solar to our electrolyzer. So we will discuss that more. So we want to have a system that can move with the fluctuations of the energy in a smart way. And we also want to reduce the chain losses on the way. So the combination of this reduces the capex and opex, and we have a favorable or cost competitive hydrogen depending on the project. So looking at transporting, what do you want to actually transport? So that's maybe a fundamental question. You can transport electricity across, but actually having transporting molecules would be cheaper over a large distance, and the energy losses are also way less. So that means you want to generate either hydrogen as much as possible locally, decentralized, or if you're also generating it centrally, at some point it makes sense to generate it and transport it via pipelines. And making it electrical, everything electrical would be very expensive. But also you need lots of power electronics in between to step up the voltage, step it down, feed the electrolyzer. But it's very simple. If you can directly connect the electrolyzer to a PV source, specifically solar panels, and transport the molecules, it helps to reduce the cost and also remove a lot of electronics from this. But of course, it depends on the specific case and depends on the project. So it's not meant that electrification should not be there or not. It's about specific applications for hydrogen. We see that Exintek really also invests in direct coupling to PV. That's one of our advantages. And we see that as you see in the figure, the actual installations, they are growing exponentially for solar power. And every year the projections, they show a decline maybe or flattening out, but the realization of solar power, that is expanding really fast. So potentially it is, and realistically the cost price of electricity from solar is reducing. So if you can have a system that is durable and you can connect your electrolyzers to that, you can put these systems down in many locations, generate cheap hydrogen, either use it at location or transport it. So this gets coupled with reduction in levelized cost of electricity from solar energy. And also similar goes with wind. But as I mentioned, we have a specific technology that is highly suitable for solar coupling to electrolysis. So to dive a little bit deeper on that, I'm showing here two different architectures that are typical of coupling electrolyzer to a DC source, that are photovoltaic PV. So either it goes via a microgrid, so you need to use an inverter step, a transformer, stepping up voltage, again, stepping it down, use a rectifier step to bring all these electrons that you produce at the solar panel to the electrolyzer. So all of these steps, they have losses, they have capital costs, they have maintenance. So we estimate if you go from this microgrid route, there are losses around maybe 9 to 10%. But some newer architectures, they have a kind of coupling between the electrolyzer and solar panel with the DC-DC converters or maximum power point trackers. These are more efficient because, as you see, there's less between the source and the electrolyzer for hydrogen production. But this still poses some challenges, especially for large stacks. So if you look at a conventional large stacks, these stacks, regardless of technology, they are not operating very efficiently at low loads. Not efficiently, but in terms of gas crossover. You're generating these hydrogen and oxygen gases at different compartments when the load drops from your energy source. And we are specifically now talking about renewable energy. So these are fluctuating energy sources. So when the sun is not shining or there's not so much wind, your energy production drops. So the system starts operating at part load, and at part load, even from 10 to 30, 40% for some systems, the gas crossover mixing of oxygen and hydrogen across these compartments is so much that you generate explosive mixtures. So what I'm showing in the left-hand side figure, they're looking at the typical solar profile throughout the day. Early in the morning and late during the day, it's not possible to purely generate hydrogen from solar energy because your part load leads to gas crossover for a conventional system. And all of these electronics that you see here, they impose a sort of curtailment loss, so-called, to this system because they have their own sizing. And these are typically not sized to 100% maximum power of your solar field. So there's some that you're always missing because the electronics doesn't allow the power to pass above a certain capacity. So you have both a curtailment loss, gas crossover losses, we call threshold losses for large stacks. So we are, with our system or with our design, we are tackling these losses. That means we want to get all of the electrons from the system as much as possible. So that brings us to our architecture. So we have moved from a large stack configuration. You can think of a stack of megawatts, or even there are stacks of 5 megawatts available or larger. We have moved to modularized building blocks. These are still stacks, but we call them modules to make the distinctions between that architecture. So on the right-hand side, you see a configuration of 120 pairs of these modules. And you can think of them that these can be individually turned on and off or modulated. That means, and these are directly coupled with strings to a copper bus bar, DC bus bar, to bring the electrons from the solar panel to the electrolyzer. And the controlling part, so the maximum power point tracking, if you're familiar with that, we don't need a centralized DC-DC controller because every single pair of these stacks have electronics, so we can control every stack independently from each other. So that means we have simplified electronics, removed them, and the curtailment losses, threshold losses, by proper sizing, we can avoid that because curtailment losses are related to use of power electronics, inverters, converters. We don't have that. We don't need it. And this also offers a significant turn down ratio. So for typical alkaline systems, the numbers in literature, they vary from 10% to 30, but I think realistic market values, 30, 20%, the partial load, it's not possible to run it safe. And the incidents also point to even partial loads as 50%. In our system, if you have a 1.2 megawatts of electrolysis capacity, every one of those single pairs of modules you see is around 10 kilowatts. So that means we can have a turn down ratio of 120 to 1, meaning that we can operate the system still within 0.8% of capacity, while a single set of modules can still operate at nominal conditions. So even though the partial load is very low, the individual building blocks and the individual units that are running the system, they are still operating. The stack doesn't see partial load, that individual set. So with this, we can modulate throughout the day. We can turn on and off these systems as many times as we want, almost. And this is kind of the distinction. We calculated this to be a 20% higher yield per per square meter of photovoltaic square area. So just to summarize the previous point, this offers a real-time tracking of renewable power. And on the right-hand side, you see our gas modules. This is a schematic, of course, but with the changes in solar irradiance throughout the day, we can regulate and modulate these individually. So that means the system's capacity can also move up and down with the fluctuations of the solar profile throughout the day. The system doesn't suffer from partial load losses, and the direct coupling reduces the need for power electronics. So these are the design choices that we have made because we are really focusing on decentralized systems. Of course, you can also connect the electrolyzers in a centralized location with a constant load with grid connection. However, advantages of using our system is really the strength is really in direct coupling with such renewable sources. So there's one thing that is very important. The devices, the electronics in the market, they are designed to regulate the power for a specific solar field to match the maximum power point, and it's called maximum power point tracking. We have measured and we have shown within our R&D program that actually the maximum power point of your solar field doesn't necessarily mean the most efficient point for hydrogen production, because at lower voltages, we see here, we can gain conversion efficiency for electrolysis, but the voltage will be lower. So we can even regulate that by regulating our control system, adjusting that to not really match the exactly at the system at the power point, maximum power point, but we can still adjust it to be a little bit at a different voltage. So we can gain improved hydrogen efficiency production. So these are all doable because we have this kind of printed board circuits that allows us to regulate each electrolyzer stack individually. So then I think I've discussed so much in the beginning, and this was kind of an introduction. I want to dive a little bit deeper into the stack and about our disruptive technology. And the photo that I'm showing here is also our Hydrogen Experience Center in the Netherlands. And I will get back to that more. Basically, what I discussed so far, I want to recap a little bit because I think it's also a lot of information. So these are the fundamental technology choices that we are making. So first of all, we are using alkaline technology. And as you may know, alkaline, it doesn't operate at an acidic environment, so the pH is quite high. So that allows us to use transient group metals like nickel, iron. These are typical electrode materials for alkaline technology. And the advantage is that we are not required to use platinum group metals and PFAS. And this also, of course, valid for conventional alkaline systems. But we generate hydrogen for now at atmospheric conditions. So that means we have a simplified balance of plant. The CapEx and OpEx for atmospheric hydrogen production is more cost competitive for us. And we have a robust control and strategy, as I mentioned, for solar coupling. And our system is very easy to parallelize for the modules. And we have a atmospheric hydrogen buffer. This is for either kind of bridging the day and night production or as a buffer step for compression, which I will also explain shortly. And the advantage is the hydrogen is produced atmospheric. For some applications like industrial warming, mixing with natural gas, you don't need to have a complex balance of plant. But for cases that you need ultra pure hydrogen, you need pressurized hydrogen, we offer a separate module that realizes the post processing part. So with that, we also kind of compartmentalize the costs for that. If there is a need for atmospheric hydrogen production, local use, then you are not paying overly for a complex balance of plant and pressurized hydrogen. So since our hydrogen production is atmospheric, it allows us to come up with a completely different design than conventional stacks. So what you see on the right-hand side is our module. We call it gas module. So from now on, I will also try to be consistent calling this gas module. It's made of polymers, except of course for the electrode materials. It's fluid and gas tight. You can operate it dynamically, and the polymers are recyclable. We don't use any PFAS type membranes or Nafion type membranes. So we use kind of diaphragm. And typical electrolyzer stacks, they're made of cell plates, and between them you have gaskets, and these gaskets are also potential leakage points. Our design is fully made of plastic on the outside. So when the stack is built and operating, there are no gaskets. So between the cell plates, we have eliminated any leakage possibility that happens if a gasket was present, and that you can think of mechanical stress or degradation. So we have eliminated that. Gas modules are nominal 5 kilowatts, and maximally they can go to 6.5, and they work in pairs. And on the left-hand side, you see, I think you recognize the conventional stacks, and these are quite large. The gas modules that we have produced, you can hold them as one person. They're around 18 kilograms. So it's still allowed within also European regulations so that one person can operate them and or change them or install them. So I have two slides about PEM and ion exchange membranes. So I will keep this brief. So it's not the core part of the presentation, but maybe mentioning briefly why we are not considering PEM. This is not about comparing the technology, it's simply how Exintek views PEM and an ion exchange membrane versus alkaline. Basically, the issue with PEM technology is that it heavily relies on iridium and platinum. So these are expensive metals. Iridium has only 7 tons of mining annually throughout the year. I think mainly South Africa and Zimbabwe, if I'm not mistaken. And it's a byproduct of platinum mining. And that's already a large bottleneck for logistics. And it's very expensive. And because the environment of PEM electrolysis is very acidic, you basically cannot use transition metals like nickel and iron because they will just be, the system will eat itself from inside when it's generating gas. So it's a matter of lifetime. And there's a lot of research going on to reduce the platinum or the iridium loading on the anodic side. But reducing anodic loading also means reducing the lifetime. So it's a little bit complicated, especially in light of connecting this to renewables, because when you connect this to renewable sources, this kind of dynamic cycles at different voltages, at low voltages, you may get current reversals, or when you shut down the system, there are ions or radicals that are attacking the PFAS membrane or Nafion membrane. You have a phenomenon like membrane thinning, pinhole formation, gas crossovers at low loads. And the PEM systems are highly advanced, but they're also highly expensive. So you need very purified water, because if there are impurities to begin with, this can really poison the metallic sites. the catalytic side. So for these reasons, we are staying away from these design choices. And in contrary to PEM systems, Alkaline allows less pure water to be used as an entry. For PEM and some anion exchange membranes, you need really ultra pure water, which is a design challenge, or also how to recirculate that. I think similarly for an ion exchange membrane, it's kind of wants to combine the best of both worlds, because it's not a acidic environment like PEM, so it's alkaline. That means you can still use transient group metals like nickel and iron, so that's an advantage. You don't have to rely on platinum group metals, but still the mechanism that allows you to transfer charge across the membrane is hydroxides, and this is also one of the degradation mechanisms that at the right conditions can also attack the membrane to thin it or to unzip the membrane. And still, the anion exchange membrane systems that are really state of the art or have the highest performance, they still use iridium and platinum group metals for that. So removing that is possible, but you go back again to a system that the ohmic resistances are really high. And so the top AEM systems, they still rely on platinum group metals. And you can run it with ultra pure water, but still the efficiency is not yet high, or the current densities you cannot really push at high current densities. So you still need to use potassium hydroxide inside the system. That leads again to corrosion. So promising technology, but in comparison to PEM and alkaline, the TRL is lower. So we are also kind of looking out for it, but it's not yet our technology or the thing that Exintek picks up for now. Going back to Alkaline, so Alkaline has its own limitations, of course, and the limitation is that you run the system at lower current density, because moving away from platinum group metals, these are highly active catalysts. So when you use a nickel or iron or stainless steel, these are cheaper, they're massive, and they're always available in the market compared to the scale that we are talking about for hydrogen. But the activity is lower, so that means the current density will be lower. So these are a bit more sluggish and massive systems, but they are more robust in terms of lifetime. Over 15 years, you can run them, and this is a proven technology. So they are a bit more sluggish in general. They can and they need lower current densities. So for our system, or at least in the Netherlands, we recently had a lot of discussions about circularity, and I thought maybe this is also interesting addition here to bring this to your attention. That for renewable systems, for new products, really the principles of circularity are becoming more and more important. So I'm discussing four of them here: refuse, reduce, retain, and recycle. So for refuse, and this is not something that we have done in retrospect. This is in retrofit. We thought about these principles when designing the product. So as I mentioned, we are moving away from critical materials like iridium, platinum, and we are not using Nafion type membranes, sulfonic acid group type membranes, polymers. And we're not using gaskets. For reduce, so we have minimal material use. We have a plastic-based design. And because the system is atmospheric, if you have worked with balance of plant for pressurized system, you would know that the complexity of the system is highly reduced when working with atmospheric systems. And for retain, we have a modular and replaceable architecture, and we went for dynamic operation. So that's why we have a large number of modules that are operating instead of a large stack, so to speak. And the plastics, the polymers we're using, they are fully recyclable. So recycling our system is, in that sense, way simpler than recycling a complex membrane electrode assembly, because mostly the system has plastic or polymer components, and we have the electrodes. So recycling that is easier. So how does the system work? So I talked a lot about modularity and that these gas modules, they work in pairs. These come now at the moment in containerized systems. So you can imagine that you are inside a containerized system. There's a corridor and you are looking on one side, and to the front of you, you have three sections you are seeing here. Every section is kind of an independent electrolysis unit. It has 15 pairs of modules with electronics, liquid circulation and cooling, which is under, and it's not visible in the picture, but basically every system here is air cooled. So, fans blowing from below. It goes through a heat exchanger. It cools the liquid and goes out at the top. So every building block is standardized. So this is basically the same design. These are in blocks of 150 kilowatts, and they are tapping from the same DC bus bar, basically. So in one container, you can have on one side 4 of these, and on the other side another 4. That makes it a total number of 8 sections, which is around 1.2 megawatts nominal capacity. And the nice thing is, because of modularity and the independent balance of plant that every one of them have, you can run each module depending on the power available you have. So if there is, let's say, only 150 kilowatt available, one module will be operating. And if there is up to 300 kilowatt, then you're operating that. So it's important to know that even within the modules, every single pair can be operated independently. So this kind of modulation allows you to really scale the system up and down within few seconds. So I'm showing this from now outside. So on the right hand side, this is the containerized system, and where you saw the gas modules happening. You see the air filters here for the ventilation system. On the left hand side, you have the power and control module, where we have the DC connection coming in from solar panels, or if we have AC connection, we have rectifiers from either the wind or AC source. And by the way, we can mix the power sources, so we can use DC only. We can also complement DC with grid power, partly, or with wind power. And the nice thing about DC is we can go from 1.2 megawatt to 1.6 megawatt. So we can really go higher because there's no power electronics between our system in between. So we can really ramp up production. The gas module is coming from the storage is coming from biogas industry a little bit. It's meant for a buffer to store hydrogen, use it as a buffer for compression step, or just temporary storage. So for example, this one is around 400 cubic meter, which is around 32 kilograms of hydrogen. Atmospheric storage. And also this kind of storage units come in different sizes. So these are kind of intermittent hydrogen buffering. So the hydrogen that we produce atmospheric is around 2.5 grade. That's 99.5% minimum pure. But for fuel cell applications, or for any application that you need ultra pure hydrogen, offer hydrogen purity at 99.999% pure. That is 5.0 grade. And this is outlet pressure of maximum 13 bar G. So this comes in addition, as I mentioned, because we want to separate atmospheric applications from pressurized applications. And this modularity comes in layers. So if we are now zooming out a little bit. So we started at a cell or a stack. We saw a collection of them. And now inside, you have this helicopter view of these gas modules inside the containerized system. And now we are kind of stacking them to build up capacity. So we have the power and control module, gas production modules, and maybe there are some hydrogen storage modules, either coming numbers or different sizes, and they can be compressed. So in this way, we can really scale it without really engineering things from the beginning. So the advantage is that you have a solution for decentralized systems. You can scale this at the speed that you are comfortable with as a business, because adding another module or adding more capacity doesn't mean new engineering and project procurement. It doesn't require, because everything is standardized, like adding Lego blocks. So the architectures, the power configurations, as I mentioned, we have direct DC between the sections, so to really directly couple them from solar panels. We can combine them depending on the source. The AC can be either wind power, which is also fluctuating, or it can be the grid. The way we regulate the system is a little bit different, but we basically we can mix the energy sources, or we can also go directly for AC. So for our system, we have maximum of 4 rectifiers in the power and control module, and we regulate the voltage for that, so we can control our production. Going a little bit higher view, how our system operates compared to conventional market is that you have all these energy sources coming to the power domain. You have the AC/DC step, and then this comes to the bus bar, and then it enters the electrolyzer. And the losses here are large because there are lots of conversion steps. Our idea is to, well, for solar, we can directly couple to bus bar. So on the lower side, you see direct connection from solar energy to the electrolyzer, and for wind, yeah, and AC sources, we need a rectifier steps to go from alternating current to direct. And what is very important, but maybe a little bit outside of the scope of the presentation, is that we carefully look at the business cases for different clients and different projects. So this, I want to show how we look at the system and energy sources dynamically, and how we look at the energy management system, because depending on the profile of the electrolyzer and the size of the solar, wind, and grid, we can offer customers different configurations, and we can offer them what is the optimum electrolyzer size depending on their available power. So in this example, we have an electrolyzer of 4.8 megawatts, and let's say the customer has a 5 megawatt solar field, and there's available 2.4 megawatt wind and grid connection. How can the electrolyzer handle that? So the electrolyzer can mix that. It can prioritize solar energy when the solar is available. That's how our system works. It can really go above nominal capacity when abundance of solar energy is available. When there's not, it can fall back to wind. And if there's no wind energy available, it can fall back to grid. So it can kind of prioritize and has a system behind it. So we can nicely calculate hydrogen production based on the power profile. And we can also see based on this profile how much is still unrealized hydrogen potentials. Then you start turning on the knobs and see, okay, which configuration works best for me. And this leads to a levelized hydrogen cost. And we can kind of see that at modular level. So this example that is shown you, you have 4 modules, 4 containerized systems, and we can see like, okay, the first one, and you can choose how you want to operate this. So this is the energy management system and the control choices. This is just one example that it goes kind of partially sequentially. So you see the first one is operating even above nominal load for the solar energy because we allow it, and the last one is becoming less and less active. So you see, like if you add more containers, what happens? If you add more electrolysis, you are utilizing less and less and less. And so these kind of insights are really important for customers to know, and for any business case. As I mentioned, this kind of analysis based on our nature of our the dynamic nature of our system, it really helps us to help the customer see what configuration works best for them and what kind of cost price for hydrogen they can expect. And this is really the decisive factor, the hydrogen cost price. And I want to just wrap up with this figure. So our hydrogen hub is in the Netherlands in Barneveld. I'm not sure if there are any visitors during a World Hydrogen Summit in Rotterdam. So if there are, please contact us. We are organizing visits to our hydrogen hub. So we'll be happy to have you. And for other occasions, also, we are regularly receiving customers. So we are also open to any people who are interested in visiting us here. And yeah, this is our information. Please reach out to me for more questions. If you have questions now, of course, I'm available. And also for later, let's connect. This is our email and also my LinkedIn, the barcode, and happy to connect and answer questions. I think that's from my end.
Thanks so much, Ahmadreza. That was fantastic. And I also really appreciate that you did include the business case and some of the pricing, because that's just something that we forget about often. So it's always nice to see that included. Okay.
And
I think
Danielle, I am on my phone at the moment. Is it possible to ask if I can ask you to share your screen with Flying High just this one time?
of course. Which one am I sharing?
Just the
The spreadsheet that we've been using?
yes.
Okay. I hope I pull up the right. You'll have to tell me which.
Sorry for putting you on the spot like this. Thank you so much.
No, it's fine. I'm not sure that we want to.
I
There's just
think
a lot of personal info in it.
actually I think the just our graphic that we have for Flying High would be
Okay.
sufficient.
Yes, of course. I can do that. While I'm pulling that up, Rich, if you're still with us, please come on and make your announcements. Apologies, I didn't see you were trying to until after I launched the webinar. Rich King, are you still with us? Is he still here? Let's see. He is here. Rich.
Hi. How are
Hi,
you,
good
my
to hear
love?
your voice. I'm
Yeah,
great.
and
How
you.
are you?
Yeah, pretty
Yeah.
cool. I didn't make any announcement.
Oh,
I'm
okay.
Confucius.
I'm sorry. Somebody in the chat said, I thought it was you, said that their mic wasn't
Okay, I'll make
working.
an announcement for you. I thought that was a superb presentation.
I
And
agree.
the other thing I would say to you is on the politics side of it, we at SAE cannot do what you were requesting because it would be in contradiction of our policy.
Well, you guys are a 501c3, right?
Yeah, exactly.
So is High Sky. So one of the things, even more reason why you should take the course, because the very first lesson in what we cover is the difference between advocacy and lobbying, and that 501c3s are allowed to advocate and lobby. They're allowed to lobby as long as it is 15% or less than their total activities. And I would almost bet you that SAE already participates in lobbying, and I could dig into that. But even more reason why you should take the course or join the cohort. So I'm happy to follow up more. That is the most common statement that we get. Is that what you just said?
Okay, so can I big you up?
Yeah.
Ladies and gentlemen, now you see how incredible Danielle is.
Yes.
Very,
Aw.
very persuasive. I've known her for some time.
I
And on
know,
that
and we
note,
haven't
I will
seen.
go.
Yes. Okay. Great. We will love to have you. And also, I can do a mean British accent too. And I did freak Rich out once when I bust out. My dad is born in the UK, so I am sharing. Bianca, can you see it?
I can see it. Thank you for sharing.
Yep. The stage is yours.
Thank you so much. So, I mean, this High Sky in general, let me actually share my video. Sorry for this. High Sky is consistently being an advocate for hydrogen aviation, hydrogen
I'm so sorry
fuel.
to interrupt, but also, Bianca, this is probably a new crowd than you're used to seeing. So maybe introduce
It
yourself.
is.
By the way, Bianca's the greatest new addition to High Sky.
Thank you so much, Danielle, for that warm introduction. Yes, so I have a passion for hydrogen aviation. I spent some time at Beyond Aero, and that's where I met Danielle. So now I am working hand in hand with Flying High, the sector of High Sky. And, our role is the speaker coordinator. So those of you who are going to be speaking at Flying High, I will be the point person for this, and just continuing to nurture relationships within this fantastic industry. And this spans into not only aviation but aerospace as well. And so I'm really intrigued by what we're doing in this sector, all the intelligent, like-minded individuals in this group. So thank you for having me speak for just a moment and share what you and I are both working on. So Flying High 2026 will be on November 4th, and we're very excited to bring together the conglomerate of not only innovators, but policymakers, engineers who are working in the field, moving forward in hydrogen aviation. This conference will not only be just a standard conference on what everyone's working on and a brief update, but from eVTOLs to startups, we're all working towards the innovation that is not only the present, but the future. So if you'd like to learn more, it's going to be a beautiful, intimate gathering. We're going to have some moments for networking and rest, but also just deep dive into the hydrogen industry. So come visit and learn more.
Yes, thank you so much, Bianca. And I'm so sorry for skipping you at the beginning. I didn't see you in the participants, but I'm like multitasking and have like 4 computer screens in front of me.
We'll make it
Sure.
more smooth moving forward.
Yes. And then lastly, do not forget to register for the webinar tomorrow. Rich, that's where you can join, is the webinar tomorrow, which I will put that link again in the chat. Sarah had a question on the I think the best use cases for hydrogen. I don't know if it was one of your earlier, maybe first slides.
Yeah.
And Sarah,
Let me-
you're welcome to come on.
Sure. Let me share my screen.
It was the most likely uses of hydrogen slide. It was a little dense. So I just wanted to clarify, should I assume that green is good and yellow is okay and red is bad?
Oh, yeah. Thank you for clarification. So maybe a little bit counterintuitive. So basically for red is you have no real alternative. So for fertilizers, ammonia, you need molecular hydrogen. So this is about industries or applications where molecular hydrogen is really needed. So in refineries, you need that for hydrocracking, removing sulfur from streams or hydrogenation, hydrocracking, breaking long hydrocarbon chains into smaller chains. So these are hard to abate sectors, so-called. You cannot remove hydrogen molecule from it. For yellow, you have alternative as electricity or battery. So for example, trucks or mobility, you can run these on, let's say, batteries. And for green, you have biomass and biogas as alternatives. So there is no real, let's say, an urgency to say hydrogen has to be there. You have other options. But and the more you go down the ladder, the competitiveness of hydrogen, green hydrogen, becomes less and less. So on top, you have industries that cannot avoid it because of the application nature of the process. And the more you go down the ladder from A to G, the competitiveness, at least where at the time this was published, it is a little bit like this for domestic heating. Maybe you want to look at heat pumps, for example, or electrification. So you're not immediately, as a business or as a private person, are looking to integrate hydrogen into that. Because also green hydrogen, the challenge is, as you may well know, is very expensive. So there are lots of factors that come into play that makes this uncompetitive so far. And the higher you are up the ladder, the more competitive it is in terms of so for example, jet aviation is almost there, but for the red ones, you still need molecular hydrogen anyways. But the question is, are you getting the molecular hydrogen from steam methane reforming, so from natural gas, or do you want to get it from green sources? Did I answer your question?
Yes, please. Thank you.
Yeah.
Thank you so much. Let me see what other questions do we
I will
have.
keep the screen then for maybe questions would be the screen share.
Awesome. Actually, I'm glad you pulled this up because I have a couple. If you could go, and I think I kind of got the idea, but when you were showing the stacks and them being modular, it was like, I don't go, it wasn't kind of towards the middle, towards the end for the cost. Let me see. Are you sharing something else? It's not on the slide.
I was maybe going a little bit fast, but
It didn't move. I wonder if sometimes it does that. Maybe you need to stop, share, and reshare because it's just stuck
all
on
right. Okay.
the ladder still. Yeah, I don't know. Zoom's been a bit buggy.
Let me try again.
Okay.
Are you talking about this slide maybe?
Yeah. Okay. So it was this one and the next one. What are the dimensions of these in feet, if possible? But
Thank you. During the presentation, I realized I'm using a lot of SI units and maybe and I didn't have the correct conversions in feet.
no, I should know them. I know them. I just didn't catch them. And so if you did say it, I didn't catch them, but no, my American brain, it would be happy to have them in feet. But I do understand SI. I just was multitasking. So you did great.
Yeah, but basically these are 40-foot high cube containers on the right hand side where the gas modules are, and the left hand side is a 20-foot high cube containers in terms of length, 40-foot and 20 feet.
And then on and you guys said you were only you mentioned gas a couple times, and I go back and watch these because I can't capture all of it. I can't absorb all of it when I'm also multitasking. But you're producing gas, but are you also just storing gas?
So the main function, every module has its own function. So the power and control module is for kind of directing the electrons to the right place, which is the electrolysis of the gas production module. So if your application is atmospheric hydrogen use, that's basically kind of the battery limit, because you can tap directly from this container and you can use it. But if for some reason your system needs a buffer because maybe you need certain volume to be able to operate, you can have atmospheric storage. And this is also a 3-layer double-sided PVC coated polyester membrane specifically designed for storing hydrogen. So one option is to temporarily short-term storage for your hydrogen and then use it. But the primary function of this is to provide a stable input for the compressor that comes after it. So it's a buffering step for the compressor.
I see.
Yeah.
How much? I guess you say it on there. How much can you store in that? How big is that? I think you say
Yes,
the different
that's
sizes, but like How much do you store like per, I don't know, like how many kilograms per
Mhm.
unit volume, I guess?
So this is the very good question. This is around the one that you see in the figure is around 400 meter cube. So in terms of kilograms, I think that is around 30 to 34 kilograms of hydrogen. So currently, this is this one system that we have, but we can order this in, or this is our product, but we can manufacture this up to 10,000 cubic meter. So it can be
Mhm,
way larger. Or
mhm,
depending on the field configuration, we can make several of them and place multiple of these units. It really comes down to the project, the landscape, how you can configure things, because these are really like Lego blocks. You can place them,
mhm,
but you need to know the sizes and calculate the distances. But it
mhm.
goes up to 10,000 cubic meter in volume.
Interesting. And then how long does it stay in there?
This is really meant for maybe order of magnitude a day or days.
Mm,
It's not really
mhm,
meant for long-term storage because you can keep it for, let's say, some weeks, but something that you need to keep in mind that nitrogen and oxygen would start diffusing into the hydrogen,
mhm,
and
mhm,
taking nitrogen out would be challenging. Hydrogen is coming from our electrolysis unit. It doesn't include any nitrogen in it, and we
mhm,
post process it and remove oxygen and water vapor from the process. So if there is a lot
mhm.
of nitrogen contamination, you cannot use it for fuel cell, because I want to be careful about the exact number, but there's this ISO standard for fuel cells, and there's certain number about ppms that if there's more hydrogen in it, you cannot use it. It's mostly about what you want to do with the gas.
Okay, I get it.
Yeah.
Okay, I got some questions now.
Hi, could you go back to your slide about dynamic costing? It was all really quite quick. Could you just go back through it? Is it that one or was it the next one? Perhaps it's the next one. I
Yeah.
lost track.
Oh, that's okay. So these are kind of the same information, or there's the same analysis, but we are looking at it different ways. So it went a little bit quickly because I'm also trying to unpack a lot of information in this slide.
Yeah.
So basically, the first one that you see here is this analysis, high level energy balance of the entire system at plant level. So this plant has four containerized systems. So the electrolysis capacity is 0.8 megawatts. That means we have four containerized systems that I have shown. But what happens actually below this figure, or the system is actually calculating at modular level for every container. And I'm showing here only the capacity factor, but we are also looking at production, conversion rate. So capacity factor means, for example, if it's one, we are using the electrolyzer at 1.2 megawatts. That means we are running the system, this module, at nominal nameplate. And the reason that it goes above it is for direct solar coupling, we can go to almost 140% of our nominal nameplate capacity. And we have some maintenance moments throughout the year planned. So there are two moments that this performance drops. And to make it a bit more visible, I'm showing the weekly trend. So the blue line is simply the 7-day average. So when you look at this with one look, you can kind of see how hard every module is working. So, and it depends also on how you arbitrage the energy between them. So in this example, you see the first one is absorbing a lot of the solar. So it's even almost always running at overcapacity. The second one is running almost at nominal conditions. And for the third one and fourth one, because the solar is running out, it's a 5 megawatt solar, but it's not always operating at 5 megawatt. So the system starts dropping in capacity factor. So you're kind of utilizing the third container and the last container less and less and less. But that's expected because we are, in this example, we are using renewables mostly, and our grid capacity is lower compared to the electrolyzer. So we cannot never really fill this, the last container. And the system is really good at arbitrage, power arbitrage. So we can tell the system which energy source you want to prioritize. But to get to the advantage of our system, we always want to prioritize solar power. So if we have enough solar, we can kind of detach the other energy sources and say, now it's time to really produce at full throttle with solar energy. And if the solar energy drops, we can start blending. So that's the strength of our system. So in this example, I was showing that. So here you kind of see how much every module is engaged. And here you kind of see this every data coming together in one graphic, which is hard to read, but hopefully it gives an idea how the system is prioritizing energy. So with the green lines, these are the solar powers, and when there's wind available, the light blue is taking the combination to fill out the capacity, and the dashed lines are kind of the nominal capacity here. And when there's abundance of solar and our system allows it, we kind of go in sort of overdrive to use solar energy only. And we sum up and this is a dynamic simulation. So we look at hourly values and we kind of sum them up. So this is kind of a weekly overview of your entire year. You can represent it different ways, but this kind of gives people an idea. Okay, if I run my electrolyzer with this profile, what is my expected production every week and how much I'm still missing. And the weeks that are dropped here, these are maintenance weeks. So we can plan everything. And these are very customer specific, but we can really plan all of the specifics of the project to give a very good advice on what they can expect from the system.
So thank you. So let me turn to a practical use case now. What kind of investigation have you done in terms of supporting the average voloport with a bunch of
Rich,
So yeah, have you actually looked at practical use cases? I'm sure you have of a voloport or a regional airport, and how many aircraft and operations you can support on the average day.
Yeah, actually, we have looked at one interesting application for ESAF, sustainable aviation fuels, and this is it can. I'm trying to see what I can share here. Basically, it's a project in Southern Europe, and we are using our technology, or we are looking into that to realize the project. From our side, we have direct solar coupling, and we also have carbon capture with another technology, and we kind of want to bring this together to generate methanol, and then from there we can generate sustainable aviation fuels. So it really comes down to the volumes and your energy source. It's not a fixed answer in a sense like this technology only supports this much, because we can scale in terms of hydrogen production or electrolysis. Our market range is up to 100 megawatts, but projects that we are looking into are kind of ranging between a few megawatts to 10 megawatts, and the sunny locations like Southern Europe compared to the Netherlands, the levelized electricity cost is low. So generating hydrogen in these sunny locations with our technology, you can also think of South America, for example, Chile, a very favorable location to tap into the solar energy. We can realize the required hydrogen amount. It really doesn't matter the application in that sense. We can deliver the hydrogen in the right amount of quality and quantity. We just need to know the specifics so we can size the system correctly.
I suppose when you produce a lot of H2, but what happens to the O2? Do you just vent it, or can you use it as something else, maybe medical or industrial oxygen, or I don't know.
Very good question. Oh, there are potential applications, as you mentioned, for medical and also for water treatment facilities. But what we see in the market, at least, first of all, oxygen is a very dangerous gas to handle. And typically, currently, oxygen is simply blown off to atmosphere. But the customer can potentially tap oxygen from us and they can use it. But for now, we don't offer any specific treatment or any specific transportation of oxygen. But as you mentioned, it's there. So if there's a use case or if the customer can use it, it's fully possible to do that. But at the moment, it's considered a byproduct, and there is not a strong business case for that separately.
And I love this question, Pierre. I don't know if it was you. I was talking to somebody last week about this very question, because I always think we could use this oxygen. And the response I got was that the oxygen purity isn't as pure as you would need it to be in medical. So one, like Ahmadreza said, you are adding an extra risk with having the oxygen around. And then two, you would have to then, purify it more and do things to it to make it a product that could be valuable in the health case. But I don't think that means there's not a market there or an opportunity there.
Yeah. Maybe I need to also clarify. Yeah, for sure, there is a potential market to it. We haven't seen that, at least in large scale in as yet. And I agree with you. For medical grade, you need to further purify the oxygen. But for water treatment, this actually seems like a great option. because you can directly mix this oxygen with water to kill the bacteria, and there are processes for that. So I think that's a big potential.
Awesome.
Well,
Thank you
it's
so
just
much.
welding. I guess a lot of people, there's lots of shop who need to buy their oxygen bottles to do their welding, with
Oh,
oxyacetylene
true.
shortages, that sort of thing. So I mean that does need to be pure. I suppose you could just, somebody's got to buy oxygen somewhere to do these industrial processes, and you guys just venting it to the atmosphere, right?
Yeah, yeah. But I mean, I think that's a very good point. And I think for now, a lot of electrolyzer manufacturers do that. But if we can get some good ideas, for sure, we are open to do that. Because for us, we are generating it as a byproduct.
Yeah, I love that. I love that you brought that up. It's something I've been wondering for many years. So with that, I want to thank you so very much, Dr. Rahbari, and to the Exintek team. We
Thank you for having me.
definitely, yes, absolutely. And if you're interested in speaking at Flying High in November, that's our annual event. Or if anybody else is on here and interested in speaking, we would love to have you. We would love to have you as a sponsor, attendee, and all of that good stuff. So with that, thank you, and everybody enjoy the rest of your week. Thanks so much for coming.
Thank you, everyone. Bye. Thank you, Daniel.
Thanks. Bye.